Now, how do we determine the molecular formula of a compound? Suppose we are given an unknown compound and we are asked to find out its molecular formula. How do we find it out? In the earlier videos in this series, we understood how to calculate the percentage composition given the molecular formula of a compound. Remember, we obtain the empirical formula from the molecular formula by dividing the subscripts in the molecular formula with the greatest common factor between them. And we understood that the empirical formula is sufficient to find out or calculate the percentage composition of the compound. So we did that in 2 steps, or you can do it directly from the molecular formula. Now, we don't have the molecular formula for this new compound. We have to find it out. So where do we start? We simply have to walk backwards here. You have to first take that sample or compound to a laboratory and experimentally find out its percentage composition. Now, from the percentage composition, we can figure out its empirical formula. If empirical formula gives you the percentage composition, then from the percentage composition, you must be able to figure out its empirical formula. Now, how do you get the molecular formula from the empirical formula? See, to get the empirical formula from molecular formula, we have to divide the subscripts with a number. Now, to get the molecular formula from the empirical formula, you have to do the opposite. That is, you have to multiply the subscripts with a number. So, to obtain the molecular formula of a compound, you need 2 pieces of information. One is its percentage composition to obtain its empirical formula, and to obtain the molecular formula, you need this number. Now let us see how we can do this with the help of an example. Now, what do we need to know the molecular formula of a compound? First, we need to know the various elements present in that compound, and the experimental process for finding out the various elements present in a compound is known as qualitative analysis. Qualitative analysis reveals all the elements present in a compound. Once you know the elements present in the compound, you know the symbols that must appear in the formula of the compound. Take for instance ethane. It is composed of only 2 elements, carbon and hydrogen. So, from that you understand that these 2 symbols appear in the molecular formula of ethane. What else do you need to know? You need to know the values of the subscripts that must be placed next to these symbols. Now, how do we figure out these subscripts? Actually, what do these subscripts indicate? They represent the actual number of atoms of different elements present in one molecule of that compound, and they also represent the number of moles of different elements present in one mole of that substance. So, to know the values of these subscripts, one thing you can do is hold a single molecule between your fingers and somehow identify different types of atoms present in that molecule and count them. But can you do that? No. Molecules are too small, so we cannot do that. So, to figure out the values of these subscripts, we have to take an indirect approach. So, to complete the molecular formula of a compound after qualitative analysis, we need to know the values of these subscripts. And for that, we have to take an indirect approach. What we do is, we take a small sample of that compound and go to a laboratory to find out its percentage composition experimentally. That is, the masses of different elements present in or per 100 grams of the compound. And such an analysis is called quantitative analysis. Quantitative analysis gives the quantities of various elements present in a given sample of that compound. So you have to first find out its percentage composition, and from the percentage composition we can figure out its empirical formula. Let us understand this with the help of an example. Say we have a colorless crystalline solid. We do not know what it is, so we do not know its molecular formula. Actually, that's what we have to figure out. Upon quantitative analysis, it was found that it contains 40% of carbon, so much hydrogen, and so much of oxygen. Now, what do these percentages indicate? They tell the masses of these elements per 100 grams of the compound. So there is 40 grams of carbon per 100 grams of the substance, so much of hydrogen and so much of oxygen. And we know the molar masses of these atoms. For carbon atoms it is 12 grams per mole, for hydrogen it is this, and for oxygen atoms it is this. And if you divide the given mass with its molar mass, you would get the number of moles, also known as amount of substance. So in 100 grams of the substance, there are 3.33 moles of carbon, 6.67 moles of hydrogen, again 3.33 moles of oxygen. If you simplify these fractions, you would get these numbers. These units get cancelled, and the unit you will be left with in each of these cases is mole. So these are the moles of carbon, hydrogen and oxygen present in 100 grams of the substance. Now, if you divide these with the smallest of these, then you would get the simplest ratio of the moles, right? And the smallest of these three is 3.33. So if you divide each of these moles with 3.33 moles, here you would get 1. These two units get cancelled, and here you would get 2 moles, and here you would get 1 mole. So what does this simplest ratio 1:1 tell us? It tells that in this unknown compound, for every mole of carbon atoms, there are 2 moles of hydrogen atoms and 1 mole of oxygen atom. Remember, it doesn't matter whether you start with 100 grams of the substance or 1 gram of the substance or 500 kilotons of that substance, because all molecules of this compound are identical. The relative proportion of the number of moles of atoms must be the same. Don't miss that logic. So what we figured out is the simplest ratio of the number of moles of different elements present in that compound. It doesn't matter the amount of compound that you started with. And this ratio also tells the simplest ratio of the atoms present in one molecule of that compound. And if you write a formula with the subscripts in the simplest possible ratio, it is called its empirical formula. So the empirical formula of this unknown compound is CH2O. It tells that for every carbon atom in that molecule, there are 2 hydrogen atoms and 1 oxygen atom. But as we discussed previously at length, empirical formula is its simplest formula, and it does not tell you the actual number of atoms of each of these elements in one molecule of that compound. Though the empirical formula of a compound does not tell the actual number of atoms of various elements in one molecule of that compound, it guarantees the ratio of the atoms, whatever the actual numbers may be. In this case, it guarantees that carbon, hydrogen and oxygen atoms must be in the ratio of 1 to 1, whatever the actual numbers may be. If there is only one carbon atom, there must be 2 hydrogen atoms and 1 oxygen atom. And if there are 2 carbon atoms, then there must be 4 hydrogen atoms and 2 oxygen atoms, so that the ratio remains 1 to 1. Again, if there are 3 carbon atoms, there must be 6 hydrogen atoms and again 3 oxygen atoms to keep the ratio 1 to 1. Now, how do we figure out the molecular formula from the empirical formula of a compound? To understand this, let us solve a simple puzzle. Say we have some apples, oranges and peaches with us, and I picked a few apples, oranges and peaches and placed them in a bag and I sealed the bag. Now the puzzle is, we have to find out the actual number of apples, oranges and peaches present in this bag without opening it. The guarantee that I give you is that they are in the ratio of 1 to 1. For each apple there are 2 oranges and 1 peach. And you can use a scale to solve this puzzle. How do you solve this puzzle? Now let us take 1 apple, 2 oranges and 1 peach and call this a fruit unit. These 4 fruits together is called 1 unit. Now what does this ratio guarantee us? It guarantees that in this bag either there is 1 such unit, or there may be 2 such units, or 3 such units, and so on. Now let us weigh this unit and say we found its mass to be 400 grams. And we can also weigh this bag, right, without opening it. Let us say we found the mass of the bag to be 1200 grams. Now what do these numbers tell us? They tell that this bag is 3 times as heavier as this unit of 1 apple, 2 oranges and 1 peach. That only means that in this bag there are 3 such units, right? So that means in this bag there are 3 apples, 6 oranges and 3 peaches. See, without opening the bag, we are able to figure out the actual number of fruits of each type in this bag. That is how we figure out the molecular formula from the empirical formula. So this empirical formula guarantees that the molecular formula is an integral multiple of it. To get the molecular formula, you have to multiply this empirical formula with an integer. Otherwise, this ratio is not guaranteed. Think about it. Now the question is, how do we know this number? Just the way we figured it out here in case of these fruits. You know the mass of this bag, which is 1200 grams, that contains apples, oranges and peaches, and you know the mass of this unit that represents the simplest ratio, that is 400 grams, and if you divide this with this, you would get 3. That means there are 3 such units in this bag. Then you multiplied each term in the ratio with that number to get the actual number of fruits in the bag. And because we already know the empirical formula, we can calculate its mass by adding up the masses of the individual atoms present in the formula. Now, if you add up the atomic weights of all the atoms in the empirical formula, you would get its empirical formula weight. So in this case, it is 30. Then to know the value of this integer, you must also know the weight of the molecule, the weight of the bag in this case, right? So that means You have to go back to the laboratory again to find out the molecular weight of the compound. Unless you know the molecular weight of the compound, you cannot figure out the value of this N, so you cannot figure out the molecular formula. So the interesting point here is this percentage composition is not sufficient to figure out the molecular formula in all cases. You can use that information to find out the empirical formula. To get the molecular formula, you need to know the value of this N, and to know the value of this N, you must divide the molecular weight of the compound with its empirical formula weight to know how many such empirical formulas are present in one molecule of that compound. And to know the molecular weight of the compound, you have to go back to the laboratory. And let us say we experimentally found out that the molecular weight of this compound is 180. Then how do you get the value of N? It is equal to molecular weight of the compound over empirical formula weight. And that would be 180 over 30, right? So it would be 6. So to get the molecular formula of this compound, you have to multiply its empirical formula with 6. Its empirical formula is CH2O, and if you multiply this with 6, by this I mean to multiply the subscripts with 6. It becomes C6H12O6. So this is the molecular formula of this compound. The interesting thing here is, even though we know the molecular formula of the compound, here we cannot identify what that compound is, because there are two different compounds with the same molecular formula C6H12O6, glucose and fructose, and that's a different story. But we are able to figure out the molecular formula given the percentage composition by mass and the molecular weight of the compound. And both of them are experimentally measured.